What better protocol to introduce first in this IC&D2 series than OSPF? And I say that only because OSPF is the most popular routing protocol in the world. OSPF is awesome in the sense that it is one of those protocols that just has so much complexity that as you move on into the CCNP track, dozens of videos will be dedicated just to this protocol and all of its concepts. But it has been moved and introduced into the CCNA criteria because even in all its complexity, it is the most popular routing protocol in the world. And by the time you're done here, you will have a very good understanding of what it is and how to work with it. The CCNP will just build on that. It's kind of like you're walking up the mountain of OSPF and you'll get about halfway up in the CCNA level, and CCNP just takes you to the peak of the mountain where you know everything. So in this video, we are going to talk about, first and foremost, route summarization. The rest of OSPF won't make much sense without understanding route summarization. We'll then move into the OSPF terms and network design. Half of the battle in OSPF is understanding what these different terms mean and why we design our networks certain ways. We'll talk about that. Finally, we'll look at the OSPF Hello packet, which is the foundation piece of OSPF that allows routers to form neighbor relationships with each other and exchange routes. Many of the concepts that we talk about in OSPF will not make too much sense without understanding the idea of route summarization. Route summarization is all about making routing tables smaller. Here's the fact. The larger your routing table, the more inefficient your router becomes. Your router is slower. And the reason why is because the router has more information to weed through for every single packet. Receives the packet, it's like, okay, you're going to here, let me look at this routing table that's just massive. This, no this. And it looks down through that whole routing table to try and find the best route. So what we can do to make our routers more efficient is to shrink the routing table. Summarization is how that's possible. Here's the idea. Let's say we have two routers in our organization. Well, we'll say mini routers, but two in this picture. Router 1 over on the left and router 2 over here on the right. Now router 1 has connections somehow to all these 192.168.x networks. We've got 00, 10, 20, all the way all the way down to 15.0. Now, with every routing protocol, router 1 is going to send those routes over to router 2. That's what routing protocols do. So router 2 will now have all these routes in its routing table, and it will say, I can reach them. And that's how we know routing. That's how routing protocols educate each other. But here's the problem with that. Router 2 now has 16 routes, 0 through 15, sitting in its routing table that it, number one, goes all the same direction to reach. There's only one way to get to router 1 in all of those separate routes. So, you know, that's the first issue. The second issue is if one of these networks go down, then that needs to be updated and replicated to router 2, and router 2 is going to have to replicate that to other routers in the corporate network because they all have the same routes, and they all need to have a synchronized routing table. Now, honestly, when we look at this picture, does router 2 really need to know that the 1.0 network went down? Now, initially my thoughts go to, well, yes, it needs to, because maybe it has traffic that's going to that. Well, if router 1 knows that it's down, router 2 will send a packet, the very first packet, to router 1, and router 1 will just reply and say, ICMP unreachable. You can't get there from here. So router 1 will take care of any packets that are going to that network because it knows that it's down. So in the big picture, it really doesn't make too much sense for router 2 to know the specifics about those networks. So here's what we can do. Route summarization is the process of summing up all these routes into fewer advertisements. I'll give you what I will call cheap summarization. Here's an example. I could go on router 1, and I could say, I'm going to advertise 192.168.0.0/16. Meaning I've pulled the subnet mask back to be a class B subnet mask. So here's what, in essence, router 1 is saying. It's saying, router 2, I know about every single network that starts with 192.168. Router 2 puts that in its routing table and says, wow, that's a huge router over there. It's got all of my 192.168 networks. Now it only really has these 16 of them, but it's advertising the whole scope. Now when you do that, the routing protocol will automatically suppress all the more specific routes. So there's no need to go and send 192.168.00/24 or 10 or 20 or 3, because all of those are encompassed in 192.168.0.0/16. It's the one big advertisement. Now that's like I said, what I call cheap summarization, because it's not very efficient. Meaning, if I send that route advertisement, that means that this router, router 1, claims to have all 192.168 networks, and I can no longer use 192.168 networks anywhere else in my network because router 1 has laid claim to them all. It says I have them. You cannot use them. So it only has 16 networks, but it claims to have them all, and we've now wasted a whole chunk of IP addresses that could be of use to us. So here's how you can do route summarization more efficiently. We need to get back to working in binary and working in our subnetting mindset. Here's the idea. I've got all of these networks. They all start with 192. They all start with 168. Now we see the difference in the third octet. Let's break that into binary. 192.168.0 is 1, 2, 5, 6, 7, 8 zeros, and then all zeros over here, right? 192.168.1 is 0.000.0.0.0.1 dot and all zeros over here. 2, I'll just kind of parentheses here, is all zeros, 1, 0. 3 is all zeros, 1, 1. 4 is all zeros, 1, 0, 0. Now we're all thinking in binary. And the same trend goes down, you know, dot, 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 dot. Let me get to, I'm running out of space here, so let me go to, we'll say 13. 13 in binary is no 1, 28, 64, 32, 16, 8, 4, 2, 1. That's 13. 14 is 1, 1, 1, 0. 15, 1, 1, 1, 1. So, looking at all this, I know it's a little difficult to see because my binary is not perfect. I should actually, you know what? I should have typed these out. Hold on. Shazam. Take a look at that. Through the magic of video, I have already typed all of these up into binary. Now, let me get back to what I was talking about. We've got 192.168, and then here's our binary bits broken up, and I put the decimal number next to it. You see 0, 1, 2, 3, 4, 5. Then down here I've got 13, 14, 15. Alright. The concept of route summarization is to take the bits that you have found that are similar, that are the same between all of these routes, and group them together. So we look at our routes right here. We've got 192, that would be, in binary, 8 bits that are all the same, right? 168, 8 bits that are all the same, because every single one of these networks start with 192, and every single one starts with 168. Now we come to the third octet, and we look, and we see, okay, it looks like all those are the same, all these are the same, all these. You can see my little lines going down. Let me actually draw a perfect line right here. Right, ka-chunk, ka-chunk, there. You see my magic dividing line? That is where the bits start to go different. So what I could say is these have 8, 16, 17, 18, 19, 20. So 4 extra bits here, 20 bits that are all the same. So the perfect summary route that router 1 can advertise to router 2 is 192.168.0.0/20. Notice I started with the very first network in my list, 192.168.0.0. So that is going to be what I start with, and 20. Now, if you're thinking about this in terms of subnetting, if I had a /20, that would be 255.255.240.0. If I were to break this into binary, my subnet mask would be 1111.0000. My increment, thinking back to subnetting here, would be 16. So, if I were to take 192.168.0.0 and I were reverse engineering this, if you will, to find out what my network ranges are, the first one would be 192.168.0.0, second would be 16.0, 32.0, and so on. So, a /20 represents 0.0 through 192.168.15.255. perfectly encompassing all of these routes that I have behind router 1. So router 2 now has the perfect route in its routing table. All of these can be suppressed. Now before I expand more on the specifics of the summarization and kind of growing it a little bit, I want to mention what that does. Number 1, it accomplishes our goal. Larger routing tables equal slower routers. Router 2 now has a smaller routing table. Second is it suppresses updates. If one of these networks go down, as I was mentioning before, router 1 no longer sends an update to router 2, and router 2 flooding the rest of the corporate network with that update, because router 2 doesn't care. It doesn't know 192.168.1.0. It just knows the big summary. So there's no purpose in sending the notification .1 is down, because router 2 doesn't really even know about the .1 network. It's all hidden. So we accomplish our two major objectives by putting that perfect summary route in there. Now, this summarization example is perfect. Meaning, in the real world, I mean, it would be awesome if router 1 had those networks behind it, but unfortunately, router 1, or our organization, just went through a growth spurt, and they just added 192.168.16.0 behind router 1.
Next.
Totally goofs things up, because 16 in binary, if I were to put it in here, would be 00010000. Totally goofs up my summarization route. Now, some of you might be thinking, well, we can fix that, right? We can take that line of yours right there. Oh, let's see if this works. Grab my line, and we could move it over. Oh, look at that. The power of animation. We can move that line over, and now you've got, that would be the first 3 bits, are the same. So my new subnet mask would be 192.168.0.0/19, because we've moved our line back a bit to catch our extra 16 network that we added down here. That would be a solution, and you're absolutely right in thinking that way, that router 2 would now still only have one route in its table. But when you move that line back, you didn't just catch the 16 route. You caught 17, 0001. You caught 18, 10010. You caught 19, 10011. Because all of those have the same 3 first digits, or 3 binary bits, and the last 5 are different. So you've encompassed a lot more networks than just 16 by doing that. Now that may be okay, but that's also, I mean, this by the way, will go down, all the way to 32, because by moving our line back 1, our new increment has become 32. So we've encompassed networks all the way up to, I guess you could say, 31.255 would be the last network encompassing this. 32 would start the next range. Now that's a lot of networks to do. So let me show you what most people will do in the real world. If you have growth, router 1 will say, okay, I've got 16. I'm going to keep advertising that summary route, the /20. Sorry, it's getting a little scribbly here. The /20 will be advertised to router 2, so it encompasses the first 15. And then I will advertise 192.168.16.0/24 as a separate route. So in that logic, it's a lot better to have 2 routes in router 2's routing table than it would be to have 17, 0 through 16. So we're still accomplishing routing efficiency, but we're not grouping a bunch of networks that router 1 does not have. So as router 1 keeps growing, you know, later on they add .17 and .18 and .19. Those routes will be advertised individually until the organization reaches the point that they say, okay, we've got enough networks behind router 1 now. We can safely move that binary line back in our summarization to a /19 and encompass 0 through 31 networks in that one summary route. So that is the idea of summarization, and that key concept is what lights the way in OSPF and why OSPF is such a powerful routing protocol. Now that you have the concept of summarization under your belt, we can move into the ideas and terminology behind OSPF. Half the battle in learning this protocol, and this is a complex protocol, is understanding the terminology and the whats and whys that are used in OSPF. And the most foundation of all the terms is the concept of area. An area in OSPF is a group of routers that all have the same routing information. So here's the idea. When you have a network that continues to grow bigger and bigger and bigger, the routing tables on all the routers begin to grow bigger and bigger and bigger as well. So what we can do is split our network into groups of routers. Like I could have mini routers within an area here. And all of those routers would have the exact same routing information. Here's a good analogy to describe it. In the trunk of my car, I have a random McNally's roadmap of Arizona. Now, also on the wall in my office right here, I have a world map. It's actually an area code tracker that shows me area codes all around the world, and it's this big world map that I can just look at and see area codes. Now, if I were trying to figure out how to get to the mall, which is about 15 miles from my house, would it be easier to use the Rand McNally's roadmap in my trunk, or would it be easier to use the world map sitting on here in the wall? Well, it'd be easier to use the one in my trunk because it's focused on specific areas of Arizona. And instead of looking at the world map and going, man, all these roads are so small, I can't see. You know, could I use the world map? Yeah, maybe. You know, if I could look close enough and they actually put the road small enough on there, I might be able to do it, but it'd be a lot harder because there's so much more information I have to read to get there. But the one in my trunk is just more focused. That's the idea of areas. Once your organization grows too big, all of your routers will have to process all that information, and every packet that they get, it's like they're looking at a world map of your organization, and it's going to slow them down. So by breaking it into areas, you could say, okay, well, area 0 represents, we'll say, Arizona. Area 2 represents Florida. Area 1 over here represents California in the United States. And we have these specific areas that group together similar routers. Now, just to give you a random guideline, Cisco recommends that an area never be more than 50 routers. So, as your network grows, you can begin dividing into areas. Now, that is a guideline. That is not a hard and fast rule. So now that we see what areas are, let's talk about the routers that make them up. Inside of the areas, and I'm going to stray from talking specifically about the backbone and types of areas and stuff like that. I want to first talk about the routers. Inside of an area, you'll have internal routers. And these are routers that belong to an area. That internal router connects to Area 0 and knows nothing but Area 0. In Area 2, I have another router. That router is an internal router. In Area 2, and it knows nothing but Area 2. These routers that sit between areas are known as ABRs, Area Border Routers. Now these are usually the beefier routers in your network, the ones that have a little more processing power, a little more memory than the rest, because these routers have the roadmaps for 2 or more areas in their routing table. So they have to be able to process and look through. It's almost like 2 pages of text rather than 1 page. The big point about an ABR that you'll want to know is that an ABR is the one that is able to summarize. Summarization. Now you know why I covered that key concept on a page ago, because if you didn't know what summarization was all about, the whole design of OSPF wouldn't make any sense. And when you're designing these areas, it has to be a hierarchical design. And what that means is that you group similar subnets in similar areas. So for example, in area 1, you know, I've got my 50 routers, and maybe over here I do 172.16.1.2.3, you know, all of these different subnets, at 5, all /24s we'll say for ease. And I've got all these different subnets. And the ABR, as it advertises area 1 to area 2, can sum that up and say, oh, Area 1 is all about 172.16.0.0/16. Yes, I'm using some cheap summarization just for ease in here, some easy stuff. But at the same time, you get the concept. The Area 0 backbone routers, they don't need to know anything more about Area 1 than that one route. So 50 plus routes summed up in one. Same thing with Area 2. Maybe this is 172.17.1.2.3 and so on. And we sum that up as it comes to the backbone, and the backbone has a hierarchical network of its own. If you don't design your network right with OSPF, It will tear you apart because the ABRs will not be able to summarize, and there's no point in dividing into multiple areas. And let me emphasize that. The whole reason that we even use multiple areas is to summarize. If you don't summarize when you break into multiple areas, you're defeating the whole purpose, and you're just causing more processor cycles on all of the routers. So when you're setting up an OSPF network, you have to be very careful where to place things. If I were to go to area 1 and just say, let's do 192.168.1 over here. Let's throw that, a 10 network over there. You're shooting yourself in the foot because you can't summarize that in a hierarchical format. That's known as an IP address hierarchy. So let me hit the specifics that I have here. All areas, the rule of OSPF, all areas must connect to area 0. That's what's so special about Area 0. It is considered the backbone of your network, and all other areas must connect over here. As your network grows larger and larger, things must tie into that area. All routers within an area have the same topology table, and if you want to all of the routers in Area 0 know everything about Area 0, even the routes that they're not using, the backup routes, and they know everything. And that's fantastic because if a route goes down in that area, the routers, wham, converge in a snap. They're able to find those backup routes that they have in their roadmap. They just pull the roadmap back out and regenerate the routing table. Now let me emphasize the difference here. All routers in the same area have the same topology table, or they all have the same roadmap. But every router within the area will have a different routing table. Let's talk about that. We'll say this router up here, this is Area 0, is represented as Arizona. Maybe this router is what connects to Phoenix. This router over here connects to Tempe, that's another city here. And this router over here connects to Tucson. So we've got, these 3 different routers. Now, in Tempe, it will have the roadmap of the entire Area 0, the entire backbone. Tempe knows how to get to Tucson. It knows that it has a backup route to go to Phoenix to go to Tucson, but it can also go to whatever this city is, Scottsdale, we'll say, and get to Tucson. It's got all this information, so if its primary route through Scottsdale fails, it just looks back at the roadmap and says, I've got another route through Phoenix.
Have a nice day.
That's meaning the same topology table. All routers in Area 0 will have a different routing table because they all start from different points. So Tempe will say, my best route to get to Tucson might be through the Scottsdale router. Whereas Phoenix will say, well, I've got a direct connection to Tucson down here. I'm going to use that as my best route to get to Tucson. So even though they have the same roadmap, they all generate different routing tables. It's just like, think about it logically. If you have the same roadmap in your trunk that somebody else has, and they live some completely different place than you, their best routes around the state are going to be different because their starting point is different. They are at a different place in the state, so they will generate a different routing table. The goal of OSPF is to localize updates within an area. Whenever something happens in Area 0, everybody knows about it. But Area 1 should not, because we should be summarizing to Area 1. And Area 2 should not. So only things that happen in Area 0 will stay in Area 0. It's like our Las Vegas mantra. What happens in Las Vegas stays in Las Vegas. Same thing here. What happens in an area stays in an area. Finally, and I talked about this, requires a hierarchical design. You must design your network right. Oh, there is one more thing. Let me erase all this chicken scratch. And the last term I want to throw out at you is this one over here tucked in the corner, the Autonomous System Boundary Router, or ASBR. The Autonomous System Boundary Router is the router in OSPF that connects to networks outside of its own. This is not another area. This is a completely different network. So it could be a network that is running RIP over here. It could be the internet, and I would say that's the most common network that the ASBR connects to.
Have a nice day.
There's many different things that this could be, but the ABR and the ASBR are the only 2 routers in OSPF that can do summarization between areas and between completely different routing systems. The last OSPF concept I want to talk about is how OSPF forms neighbors. Unlike the RIP protocol, OSPF will form direct neighbor relationships with the routers it wants to speak with. script just walks up to the Ethernet line and says, hello everybody, sends out a broadcast to everybody. These are the routes I know about. It doesn't actually form neighbor relationships, it's just the other routers happen to hear it saying, hello everybody, and adds those routes to its routing table. They don't know about each other directly. So, in OSPF, routers come up to each other and say, hello router, hello, and they start exchanging routes between each other, and then they maintain that neighbor relationship using something known as the hello protocol. It's not just what I'm saying, that's the technical name of the protocol. Now, hello messages are sent when you configure OSPF on whatever interfaces you designate. So if I say dead out serial 00, then it will start saying hello and trying to form neighbors on that interface. If it does, these neighbors will meet and they will exchange routes, and now we have a synchronized routing table. In OSPF, these hello messages are sent once every 10 seconds on broadcast or point-to-point networks, and once every 30 seconds on non-broadcast multi-access networks. Those are things like frame relay, which we'll talk about later. The idea is that the more often you send hello messages, the sooner you will know if a neighbor is down, because they'll stop responding to your hellos, and the faster you can change over to a backup route. Now, a lot of people in the OSPF world will tune this hello timer down to a second or maybe 2 seconds. So you're just sitting there going, hello, 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 making sure that they're online because you want to be able to detect that failure extremely fast. Now, when you and I say hello, we think of a greeting, like, hello, how are you doing? Or something to that effect. But when OSPF sends a hello, I want you to think about it like an envelope with hello written on it. And when that hello message comes across, the router opens that hello envelope and sees all of these specifics inside of it. It will see things like the router ID, which is the name of the OSPF router over here. It says, hello, my name is, and the router ID is an IP address. It might say 1.1.1.1. The router will say, well, hello, I'm 2.2.2.2. That's the router ID. In that hello envelope will be the hello and dead timers, meaning how often they're saying hello, and it's kind of rude, but that's all right. It's how soon until they believe you are going to be dead. You know, how many hellos they can miss before they say that person must be down. They will advertise their subnet mask in that hello packet. They will advertise what area they are in that hello packet. Now you notice some of these messages, or I should say pieces of that hello envelope, have little stars by them. The stars, if I were to put a little key, star equals must match. Alright?
Next.
They have to match in the hello packets between the neighbors, or else these guys will not end up forming neighbor relationships. I think about it this way. My old roommate that I used to live with actually met his wife online. He had one of those dating sites. I don't know what they call it, where you match up, right? And when you go to this dating site, I actually was working with him because I'm the computer guy of the house, and I was showing him how to get on there and log in and all that. And on this dating site, you have criteria, and what you do in your criteria, you say, okay, this must match. For instance, this person or this mate that I'm looking for must have blue eyes. They must have an adventurous spirit, meaning they like to do adventurous things. They must have, and you list your must-haves, and then you list your, well, it would be nice if they had pink painted toenails. I don't know. I'm just throwing stuff out there, But, if those don't match, it's okay. In the same way, our routers are online daters. They're sending their little hello messages with each other, and inside of there are criteria that must match. For instance, if this router 2 over on the right-hand side says hello once a second, and the one over on the left says hello once every 10 seconds, then it's going to say, I'm sorry, we don't match. We're not compatible with each other. And at that point, they will choose not to form a neighbor relationship. Now, a lot of these things that you see in this hello packet, we haven't talked about yet, and we will talk about. But the ones with stars, if they're not matching, the neighbor relationship will not work. And that's the #1 troubleshooting criteria we have with OSPF, is making sure that all these things match. Otherwise, routes won't be exchanged. That should be enough of the OSPF concepts to get us going. As we continue this in the next video, we'll be able to see how these concepts apply in our configuration. But before we do, let's wrap things up here. We first off looked optimization at its best, or the best way to optimize a router is through route summarization. We then moved into the OSPF terms and network design, and to hit the high ones, area is the most critical. Area defines routers that have the same topology database or roadmaps. ABRs, area border routers, is what moves you between areas, and ASBRs, autonomous system boundary routers, are the routers that move you outside of your own OSPF network, maybe to access the internet. We then finally analyzed the OSPF hello packet. The hello packet is the foundation language that these routers will use to communicate with each other and form neighbor relationships. If the relationships don't form, routes won't be exchanged. I hope this has been informative for you, and I'd like to thank you for viewing. What better...
Have a nice day.